Okay, this is going to be a lot of fun. CERN claims they can see the influence of gravity on antimatter. All right, so how did they create the antimatter, and what does it do with gravity, and what has it got to do with my electron flood theory and my model of a proton versus their model of a proton, and my model of particle spinning light particles compared to their wave theory, and my possibility of getting free energy. Let's start with observation of gravity on antimatter. So how do they get the antimatter, and how does the gravity affect it? This is kind of funny. I'm just getting ready to get my video going, and this pops up on top of my screen: Science Tech Daily, Physics Unraveled, Accelerating Waves and the Mystery of Time and Relativity. And they're showing like a well of these waves coming in. Right now, this is not well understood, and I'm going to show you, I think I have a pretty good understanding of this. And what we're going to see is Dirac neutrinos, the black and white particles. They call it antimatter and matter. What I was going to do today, and I am going to, is talk about CERN's latest thing where they're looking to see how does gravity affect antimatter. So how do they produce antimatter, first of all? And secondly, can I show Dirac neutrinos? And yes, I can. And here they are right here. These two particles together, which Fermilab and CERN, they all know they're there, but they really don't know much about them because they get them in from big, huge debris. We use light, and we can see them separated away magnificently, as you can see. It has the red, glowy edge around it, but that particle never changes size. And they know that at CERN. That's exactly what they said at Fermilab. It's a fixed particle. This one gets big and small, as you can see. And this is a photon of light. And again, I'm going to be showing this, and then I'm going to show that this is literally a nuclear explosion. It's a subatomic explosion. Atoms, big balls of atoms that blow up, and they throw off huge chunks of hand grenades. Really, that's what hurts you. This is light. So we're splitting them. We've separated the black from the white. That's fission, and when it comes back together, it's fusion. Not only that, this is the Whistler waves, which I'm going to explain to you very well. And you see how separated they are? See how tight they are back here? Total difference. And these are almost in the audible range, which you actually hear them go, and then comes the blast. And then I'm going to show you that very clearly in an atomic bomb. So these are the two particles. Normally they were attached together, like this. All right, they're always attached together. They never come apart. And to rip the white away from the black is very, very hard. That's what generating electricity is, to create strictly the white, because that's what fills up the batteries in your car or any batteries. It's electricity. And it has no weight to it to speak of. None. Your batteries run for 500 miles, and when you go back and charge it back up, it didn't lose weight, it doesn't gain weight. You know, just the tiniest bit. They say, it's inconsequential, but it isn't, but it is. You know, it's almost no weight at all, because this has no weight. Just as I show you soon how it just burns a house up, and it doesn't even move the house until the black particle comes. And here's what we did. We took that black and white particle right there and shot that through a Venturi right here. And when it came through the Venturi, or as it started to come through the Venturi, the black couldn't get through. The black is not changing. It's one big ball. It's like a bowling ball. I can't get through. The white can get squirt through like a cotton ball, just squirt right through, and then it puffs back up again quick. So everybody get away from me. But it can squirt down like this. But when it's down tight like that, boy, she's got a hell of a lot of energy. When it comes out the other side, boom! And that's when you get these electron showers that can go into trillions of electron volts. There's no reason we can't use this to get free energy. These are the right particles. Now, I'm going to show you in great detail about the antiprotons, the antiparticles, and all of that stuff. So hold on to your hats, because here it comes. And it all relates to the Dirac neutrino, which is the black and white particle, which is this black and white particle. That's what it is right there. And then I got all kinds of stuff to show you. And they say that if you can do this, which we did, the muon neutrino and electron neutrino attached together, the black and white, You separate it, the muon goes on its own, the electron goes into showers, and if you can do that, all bets are off in physics, and that's correct, because the only thing that works is electron flood theory, dipole electron flood theory. So we're going to go into that, and this is a proton. A proton is not one big ball, solid ball that you can smash into little bits and pieces. It's 1,823, I believe, dipole electrons, all glued together. At that point, it becomes solid, really tight. For some reason, there's some kind of a vibration resonance in the universe that it has to be. And at that shake and vibration, bang, it locks in. Because if you ever see the salt table experiments, it does the same thing. At a certain vibration, the molecular complexity gets huge. Well, I'm going to show you. All right. Pay attention to the details here as I explain it. This guy, Jeffrey Hangst, who I contacted, and I'm hoping I'll hear back, but I'd be surprised, but who knows. It says, in physics, you don't really know something until you observe it. Exactly. You have to observe it. And that's Jeffrey Hangst from CERN. And this is the first direct experiment to actually observe a gravitational effect on the motion of antimatter. It's a milestone in the study of antimatter, which still mystifies us due to its apparent absence in the universe. It's not absent. It's there. It's just that it's attached to matter. And that's the problem. It's not just something totally separate. It's part of the dipole electrons. It's part of that. There's a positive side and a negative side, yes. A glowy side and a dark side, yes. And every electron contains dark matter. The dark matter is attached to the glowy part we thought was just the electron. There's two pieces to it, and I'm going to show you in great detail, and I will unmystify this right now. Okay, there's not a whole lot to talk about here but about the antiproton, but remember this guy's name, Dirac, Paul Dirac. He got his Nobel Prize in 1933 for predicting the existence of a positive and negative, which means a dipole. And this is the antiparticle of the proton. And it's stable, but very shortly lived. And that's because the black particle wants to be attached back to the white particle. These are what they would consider the antiproton and proton, only we're down in the electron range. So we have a negative electron and a positive electron. Together they form the Dirac neutrino, and I'll show you. Now they're talking about them as being dark photons and all this since I've been showing this stuff. Because I can show this stuff. Nobody else can show it. And the first thing they say is you can't believe any of this stuff until you actually see it. And that's what we're doing. I'm showing. So, believe it or not, I'm showing it. Don't forget, this is CERN declaring they've seen anti-gravity. In physics, you don't really know something until you observe it directly, and that's Jeffrey Hangst. He's from Denmark. And I think I might have mentioned this. I did send him something with a whole raft of our pictures of these experiments we did using light. So the light is light, and you can see it. So there's no little drawings and so forth and CGI or any of that. What I'm showing is actual factual pictures taken with CMOS, which is complementary metal oxide silicate photo receivers, and we're actually picking up these photons and these glowy little particles, and that's what I'm presenting to you is facts. All right, this is kind of important to understand. I'm going to show you Whistler waves, or I have shown you, which precede atomic bomb blasts. And also our light experiment, we show the Whistler waves there as well. Now, what is causing them? It's an electron interaction with dipoles, with dipolarizing flux bundles. Well, let's just go with it's an electron interaction with dipoles. The electron itself is being pushed. Not the dipole in the Whistler waves. It's only the electron, and I'll show you that. Normally, both of them push together because they're stuck together. But when we can take an atomic bomb, or you can get in the outer atmosphere where you have a hell of a collision, where they say this is in the outer atmosphere of Earth's outer atmosphere, the lower part of the magnetosphere. So outside it's getting really scrubbed and creating a huge amount of magnetism, and then it's pulsing down below, creating these rapid earthward motion of plasma, boom, 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 within dipole flux bundles. All right, increasing dipolarization of the magnetic field. It keeps getting boom, 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 boom. Now, the electron heating is evidence near or within dipolar bundles as rapid increases in energetic electron flux, up to about 100,000 electron volts. It is often referred to as injection. Well, injection means they're injecting electrons forward. Boom, 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 electrons. And I can show you this happening in our experiments and in an atomic bomb blast, because our experiments are nothing more than a nuclear bomb blast, a nuclear explosion. I'm not kidding you. Okay, this is the atomic bomb blast, shown many, many times. All of these wires, poles, everything that can burn will burn up. All the shingles, the house facing, and so forth. Whatever normally would burn up by being radiated will burn. Metal cylinders and so forth will not burn. Now watch what happens as this happens. You're going to see two events. The first is just a huge glow, and then everything just burns up and it just smokes. It doesn't even move. It just smokes up. That's the injection. That's injection. Then the black particles come and knock the house down. All right, I'm going to play it right now. It's running in slow motion, so here it goes. The first thing you're going to see is just the most brilliant glow you can imagine. There it goes right there. So everything now is just smoking up, not even moving. The poles, the wires, you see it? I'll stop it just so you can see. The metal things will not burn, and the things that are not in the direct line of the bomb blast, they're not going to burn either, because they're not being irradiated. But anything that it hits up against, it burns. Now, the reason that the camera doesn't burn up and get destroyed is it's in a hardened enclosure facing away from the radiation. It's facing in this direction, so it won't get damaged. Now, this is going to burn all up, and all of these wires and the poles and everything, but they don't move. Again, there's no mass to this white energy, and this white energy, the glow, is exactly what you put in your battery. It has no mass to it. When you force it into your battery, you got tons of electricity. All that glow goes down into your battery, and then you can let that feed that glow back out to make your motor run, or make your car run, or your whatever you want. Electricity is electricity. You know how it works. But you have to get that white away from the black, and that's what's happening here. This is nothing more than pure raw electric power. That's all it is, electrons. That's all it is. This is white power. That's it. The next part will come, and that's the black portion that will knock the house right down. So here it comes. Still smoking, still smoking, still smoking. Everything's burning, burning, burning. It's just dust, just boom, there it goes. All right, so what did we see? We saw everything burn up from the white, and then the black came and knocked it down. Can I show that in experiments? Absolutely I can. All right, here's where we're going to hear the Whistler waves, and this is another nuclear bomb blast. And preceding the explosion, first thing you're going to see, they're counting down. Way down in here is the bomb. They're, I think, 3 miles back, something like that. I'm not sure. But what you'll see is an enormous, just a flash, and then you're going to hear, and then nothing. Dead silence. And a little while later, that wave will come across, and that's just like hitting the house. So the first thing is going to be the Whistler waves, which is just like the house burning up, and then this wave will come and hit us. Now listen to what's going on. Did you hear it? Now, nothing will happen at all, but the black wave is coming across the desert floor. See it there? You see it coming further and further and further? And it's coming at them. All the people are saying, wow, that's cool. And all of a sudden this is going to hit, and it will knock your socks off. And then there will be a rush. Get ready for the shock wave, because they're seeing it come. You see it? It's coming. Get ready for the shock wave. And when it hits, now listen to what happens afterwards. All of that rush is coming to keep pushing that house down. You hear it? All right, so what? I'm just going to stop it right there. So what did we witness? We witnessed the thing, and then we heard, what's that all about? And then nothing, absolutely nothing, until that wave, shock wave, hit. So can I show that in our experiments? Yes, here it comes. All right, this is outrageous. It really is. This is a salt table experiment, and what that means is salt is a polar molecule, NaCl, both sides of the periodic table, and they put it on a flat plate that's going to vibrate it like crazy at different frequencies, and then the salt finds a way to become stable at an exact frequencies. Now, Tesla talked about frequency and vibration and energy. Well, frequency and vibration is literally the energy. All right, so it's not all three things. Its energy is really frequency and vibration. That's what causes energy, is when it's bouncing back and forth against each other. These white particles. That's what energy is. The higher the frequency and the harder the vibration, the more the energy. Basically, as simple as that. So let's look at this. This is really amazing. The first time I saw this, I was absolutely blown away. Hold on. Okay, this is Bruspup on YouTube. And what they're going to do is put salt on this table, and then they're going to vibrate that table using a oscillating, vibrating electrical impulse. And what does that mean, vibrating it? It means you're pushing electrons up and down, electrons up and down, electrons up and down, electrons up and down. And what is that? That's a resonance frequency. And when you get a frequency, it means how many pulsations per second. The salt will lock into a certain pattern. And that's what's happening with particles. The first particle, and it's almost identical to the periodic chart. It just blew my mind. You see way up here at the top of the chart, you could only have, here you got one, or this layer right here, think of it this way, can only have a maximum of 4. Okay, it can only have a maximum of 4 electrons surrounding the core. After that, you go up into the rule of 8, and they want to have 8 surrounding the core, but they get more and more and more and more complex as they come up through here. So that means you have more and more and more balls, basically, of zones of magnetism. And that's exactly what you see. It's just stunning, really. I mean, just unbelievable. So they're going to start out in the smallest, well, I'll explain it as we go along. Let me turn the sound down a little bit, and I'll try to explain it as we go forward here. Now, what they're going to do, the smallest frequency they have is going to start out at 358, I think, something like that. Hold on. Here they put, okay, you see salt. Salt is NaCl. Well, what does that mean? NaCl. They're both sides of the periodic chart. That's a polar molecule, positive and negative. So it's nothing more than a little tiny bar magnet almost. It's in that range. Think of it that way. Now, so what is going to happen? As these electrical signals bounce back and forth, they're bouncing actual electricity up and down. So they're all responding at the same time as that pulsation comes up like that. It's not like a random, just every now and then one will bounce here and there. They should all be bouncing until they hit a certain boop frequency and they lock in. And that's exactly what happens. Watch. All right, so they put that down. Now, they're going to vibrate the metal plate. That just means positive, negative, positive, negative. The pitch of the tone increases. The jetron patterns will form more complex. Now, all right, here we go. 345 hertz. Watch what happened. There it is. I'm going to stop this. What are we looking at? What is it that we're looking at? That's the core. All right, and these are the zones that the electron can occupy, and it's only 4. And that's exactly what you would expect in the hydrogen-helium range. Then it goes up to the rule of 8. You still have a core, but you're going to have 8 surrounding it. And watch what happens as they go up in frequency. It's just unbelievable. All right, so that's locked in at that frequency. Now look, now they're going up to 1020, 1033. Look at this. Look at this. 1, 2, 3, 4, 5, 6, 7, 8. That's the rule of 8. And now here is the core and the 8 electrons surrounding it. Now, it goes up from there and gets more and more complicated as you go up into higher and higher frequencies. But it's still all very stable. And if you look around real careful, you can pick up on the rule of 8. You see this pattern: 1, 2, 3, 4, 5, 6, 7, 8. And then, of course, the core. And it gets, look at these out here. I'm not going to go through the whole thing, but look at this. Look at how complicated these things get. When they get higher and higher in frequencies, look. Look at this thing. But you can still see the rule of 8. It's almost always a 1, 2, 3, 4, 5, 6, 7, 8. It's always like a grouping around the core as they get bigger and bigger. And that's what allows molecules to interact with each other. So you've got 2 molecules here, or 2 atoms basically. And they have, this one has like a couple of extra ones hanging off the side, and this one has 2. And they come up and they just attach like that. And then all of a sudden you have a molecule. And then another one will come along and it'll dig its way in because there might be another vulnerability until it gets to a nice complement of particles that make it very stable. And then it still will break down. Anything can break down. Enzymes specifically in your body break things down at an unbelievably rate. I mean, just absolutely stunning fast. An enzyme creates enough interaction with these little particles that it would take a year or more to do what it does in under 1 second. I mean, way less than a second. It's just instantaneous because it's working with all these little particles and nobody knew it were there before. They just never knew they were there. They thought it was just 1, 2, 3, 4 like that, with protons and neutrons. No. Every proton is made of 1823 of these little dipoles, and the neutron just 1 more because it becomes neutral at 1824. And then just like this, at that frequency, it locks in, and the frequency has to relate to the number of particles. The number of particles is dictated by the frequency. Basically, that's it. And I can't, there is a lot of things I really can't account for, to be honest with you, but I can tell you what, this stuff is just stunning. Look at this. As we get up into higher frequencies, boom. But you can always see this. 1, 2, 3, 4, 5, 6, 7, 8. and it just gets bigger and bigger and bigger. So there's something going on with the frequency versus the quantity. So there's some equation you could probably have saying the quantity of electrons relates to the frequency, and it does. 5907 makes this number of particles. There's a lot to think about here, but this is a lot closer than anybody else is at right now. All right, this is absolutely fabulous. This is Latham's Crazy Machines. And what he's doing here, he's got a brass ring, which has no polarity to it, no magnetism. And he's putting in 6 niobium magnets. All right, and they have a polarity to them, just like any bar magnet does. These are nothing more than bar magnets, but they're very powerful. Neodymium is very, very strong. Now, watch what happens with these 2 bar magnets. All right, can you see that down there? I believe you can, yes. All right, watch as I put them together. Watch what happens. Boom, they come together. That's what bar magnets do. However, if I was to change the polarity of this one, now watch what happens. It pushes that one away. You see it? Now, if I put this one this way, it comes back together. So it depends on the polarity, which side you have facing which piece. Because right now, I really almost can't push these together. They're so hard pushing back. I'm not kidding you. I'm pushing hard. I'm pushing hard. And you know, I'm going to demagnetize it. If I push it too hard, it will destroy the magnetism in it. But trust me, I've already damaged it, I think. What he's going to do is put these in one polarity, and then he's going to take, as I will show you, here goes. Let me open this up. So he's got this all set up to go. Watch what he does. I'll try to explain. All right, he puts it down. He takes that one. See that? You see how hard that pulled against there? That's like these two coming like this. All right. Then he's going to take it apart, and instead he's going to turn it this way. So now they push each other apart. Okay. However, there's going to be one in the center that's going to suck so hard that on any other ones that comes in is going to want so badly to get to the center. It will try, but these will push it away. Watch. This is just unbelievably cool. Called tractor beam magnets. So now he tips that upside down. He puts it in the center. So now what does he have? He has an extremely strong positive, and he has it surrounded by 6 negatives. So if another one comes in to want to get to that extremely strong center, it will be opposed by these, and it can't get there, so it will hang out there, but it'll just always be trying. And that's what's called the valence electron. All right, so here we go. He comes up with another one. All right, watch. Boom. See what it did? It didn't hit. Same thing like I told you. When I push these, I can't hardly get them together. I'm telling you, you can't. You know, at the end, they will do stick here, but going face to face, they just won't do it. And because he's got a round magnet, it's coming face to face no matter where it is. And it's being pushed back by these. And it will hang out into the middle of the field. See these two magnets here? It will either be right in the middle of that field, or right in the middle of that field, or right in the middle of that field, because they cause fields to surround themselves. They're bubbles around it, basically. And this will sit in between those two bubbles. If you look really carefully, you'll see. You see? It's not floating around just anywhere. You see where it is right there? Right in between the two bubbles. All right, so he's going to shake it, and when he does shake it, it still stays there. See it? It won't move anywhere. It's staying between the two bubbles. The two bubbles have it held like that. And it's tight in there. It wants to get into that center core. All right, if it flips over, it's going to attach to this. And I think it does at one point. It does flip over. When that thing escapes from there, all right, let me just explain something. As he's shaking this here, that's heat. That's heat. And as it escapes, it's going to be light. So watch. Boom, there it goes. It just turned into light. There it goes. Once it's separated, it's on its own as light. All right, which is a particle on its own that normally would be attached to that 1834 or 23 particles. But now there's one on its own. Normally there's two of them. The two of them would come together, and they're two biomagnets make a photon. All right, and that's what leaves the mass to create light. And it gets bounced off of there. A lot of times they'll get bounced off. You see how he's going bounce, 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 and it's going boing, boing, boing. But if you hit it hard enough, boom, it comes out, and it comes out as light, and that's what we see. All right, just so we're all on the same page, that's light, not accelerated yet, just starting to accelerate. It is glowing all of the particles in front of it because its field has to push through. That's called a wave. The particle is back here. Now, the particle is that little dot right there streaming forward. And it exploded here at the Venturi, and it actually pulling itself, just like a jet fighter, right out of its wave, exceeding the speed of light, then crashing and exploding, and the black separates from the white. And here is the black and the white right here. All right, there's the black and the white. And that's a photon. Prior to that, they're neutrinos. Neutrinos don't have this full energy of a photon. They're just about getting ready to charge up. These are neutrinos. The only reason this one here is just like that, because it's exactly going through the Venturi. It's exactly in line with the Venturi. And I'll show this in a little more detail. Now, again, light, light accelerating, light smashing. There's the two particles together as a photon. When they come through here, they come through, only the white comes through all by itself, just a white particle, because the black separates, it stays back. And I'll show you that in much more detail right here. So don't forget, the particle was coming down in a black and white state, attached together, two dipoles together. The black stays this side. The white is shooting through here like a rocket ship, because it's now disassociated from the white, and it could just flow like smoke. I mean, you saw what it did at the house. I'm sure I showed you that, and it just floated up. So it can be pushed by the black, and it's going to be pushed, and this is pulsating, so we can pulse, and just squirt that through at our own leisure, how many pulses we want and how intense the light is going to be. All of that relates to voltage, amperage, all of that stuff. Now, right here is raw energy, and again, I think I mentioned, this is the only thing that you want to put in your batteries. You have to pull that black away from the white to get that white into your battery. It has no weight to speak of. As I showed you, the house didn't move. There's no weight there. There's no push to it. So it fills your battery up, and your battery doesn't get any heavier to speak of. But you can drive another 500 miles. All right, so that's the key. We need this, and we can get that, I think, and put it into a solar collector right here. You know, a nice one, something good, because we don't have to be out into the elements and all that. It's going to be in a little shoebox. Hold on, something similar to this old Geiger counter that I have here. All right, so you put it in a box like this, you carry it around with it. You dial in anything you want. Of course, they don't have dials anymore, they have buttons. So you're going to have all your different outlets in here, AC, DC, frequency, 60 cycles, 50 cycles, AC, like I said, AC, DC, USB, anything you want coming out of here. And because of the amount of energy that we should be able to get out of there, I don't see why you shouldn't be able to power a car or a house or anything with about this much of a unit. And this is all solid state. It's almost dirt cheap. Literally, this stuff is just little lasers and photo receivers and solar collectors. They're just a dime a dozen. And already all this other stuff exists, which is your battery stacks and your voltage regulators and all that stuff. That's done. All we need to do is do just like I'm showing you and get that laser going through to a collector. As far as I'm concerned, that's it. Because we didn't have any extra energy whatsoever here, because we're working with light, and it didn't break anything. It's not eating into anything, because we're only working with the smallest particles. We're not hitting things with grenades. When they did all of their work at CERN and all those, when they smashed those particles, they hit things with things like this. And that damages things, yes, obviously. At a bazillion miles an hour, you whack somebody with that, you're hurting. But if you're down here at a bazillion miles an hour, it might give it a little damage, but I don't think much. And plus, it's not going to stay apart from each other. They come instantly back together. That's fission, that's fusion. And the fission, they want so desperately to be back together that they jump right back together. But if we put a harvester here and just forced it down through a photodiode into some kind of a harvester, a battery stack or whatever, or you could just run right out of it into a driver, just like your electricity in your house. You know, it would just continuously be feeding electricity to those circuits. Anytime you turned it on, the lasers would go, and then depending upon how much energy you needed, just more and more would turn on to feed your outlets. So you may not even need the batteries, you know, because the batteries are going to add weight. Pretty much. Lithium is pretty, you got a lot of energy for the least amount of weight that I think of right now. But if you don't even need the batteries, wouldn't that be better? And all you'd have is, like, say, 1,000 of these lasers. You could put 10,000 inside of a little box I showed you. These are so tiny, it's just incredible. And you could just have them turn more and more on as you plug more and more things in. Simple as that. No big, huge facilities to run these things. You could just carry it around. All right, I think I showed you the atomic bomb, and this is exactly what happens. They use uranium or plutonium, and it relies on fission. That means it breaks apart. The white goes first, and then the black comes. It's a nuclear reaction inside the nucleus, in which a nucleus or an atom breaks apart into two pieces. As long as it goes into two pieces, that's fission. When it comes back together, that's fusion. All right, this is the International Atomic Energy Agency, and what is fusion? Fission is when they break apart, and that's the atomic bomb. Fusion reactions takes place in a state of matter called plasma. That's that white particle state. A hot, charged gas made of positive ions, I don't necessarily go with that, and free-moving electrons with unique properties distinct from solids, liquids, or gases. It's a plasma. It's the particles have separated the black from the white, and that just does not happen naturally. All right, you see this? Why are scientists studying fusion energy? Ever since theory of nuclear fusion was understood in 1930s, scientists, increasingly also engineers, have been on a quest to recreate and harness fusion. To recreate fusion and harness it. That's because if nuclear fusion can be replicated on Earth on an industrial scale, it could provide virtually limitless, clean, safe, and affordable energy to meet the world's demands. We can do this right now, and it doesn't have to be on an industrial scale. It can just be in the hands of everyday people, as long as it's not dangerous, and it shouldn't be. Clean, limitless, clean, safe, affordable energy. Coming back together, it's just coming back together. That's just what particles do, and it's not going to harm anybody. And when we're down in the light range and breaking them and coming back together, there's no chance you can get injured, but you can get a hell of a lot of electricity. Okay, this is about gamma rays, and gamma rays are the things that hurt you, and they're the things that can damage you. Now listen to this.
By nuclear explosions, and even by the lightning and thunderstorms.
Hold on one second, let me come back here.
Radioactive decay. All
right, gamma rays are created on Earth. Let's look again. Gamma ray sensors above the atmosphere are deadly to humans. Gamma rays are what kills tumor cells and so forth. They use it for targeted destruction of cancer and so forth. Now listen to this now.
Atmosphere, deadly to humans. Gamma rays are created on Earth by natural radioactive decay, by nuclear explosions.
By nuclear explosions. Basically, that's what we did. We created a subnuclear explosion, separated the white from the black. That's what the black is, the gamma rays.
And even by the lightning and thunderstorms.
Same thing with thunderstorms and lightning. The lightning is the white part being stripped away from the black, creating gamma rays. All right. Fully understand this. That's the Dirac. There's a black and a white, and here they are coming into the Venturi, and it separates the black from the white. And we can see that the black pushes the white. You see the black pushing the white, and remember, this is those Whistler waves, which are very long frequencies versus the very short frequencies that create them. And these are only being created because of the push of the white. There is no black particles involved in here. It's just a of the white, and it makes that little blip. Now here there's black bump, and then the black is in here thumping the white ahead of it. So there's two different phases of the energy, and this is extremely high energy. Now if we continue to increase the vibration here, we'll push the white completely away, and all we'll have left is the black. All right, so you know these two, black and the white, were attached together, and when they hit the Venturi, we could separate them. So we have extremely high energy, and the black particles are separated and don't go through. And we can see them, actually the black ones pushing the white, and this is exactly like the house being burnt down. So this is virtually a subatomic nuclear explosion. There's no difference whatsoever. The Whistler waves come first, the burner wave come next, and the knock down the house wave comes next. All right, let's talk about radiance. You see this? This is the amount of radiance. This is more and more and more radiant, you see? It starts down here, and these are the wavelengths, how long the waves are. And the tighter they get, the more energetic they are, and the more radiance they give off. Well, why? Radiance is the white particles. Only the white is the radiance. The black particles is just, they're the pushers. So it pushes faster and faster and faster, and then you get up to a point where you can't push anymore. All of the white ones are gone, and it just drops right to zero. All right. Oh, there's no more white particles. Now all you have is the gamma rays. Now is where you got the power to knock down houses. All right, because you don't have any white particles left. That's gamma rays, and if you can concentrate those, you can, and they will concentrate because they don't mind being right next to each other. The white will push away. The black will just concentrate into a beam, and they don't understand it. They talk about black body. Yes, it is exactly black body. But then they come down here, nobody's got all these formulas, and I don't like formulas because they just don't work. Once you make a formula and rules and laws and constants, it doesn't work. The formula misbehaves at higher frequencies. That's because there's no more electrons left at that extreme frequency. They're gone. See, this is the matter, antimatter. They just don't understand it. And they're talking about it occurs naturally in high energy processes like nuclear explosions and extremely high energy accelerators. Well, we did a high energy accelerator, but it was just, kind of micro. See, Jesse Grant, they're the ones that did all my CAT scanning. They did 7 CAT scans for me. Now, it produces minute quantities of antiparticles, which are the little black particles, resulting in particle jets. They'll stay right together, which are immediately annihilated by contact with nearby matter. The white particles suck them right back in. I've shown this absolutely without question. This is exactly what they're talking about. Here it is right here. They come, they separate. The black separates. The black is antimatter, and it reunites immediately with the white to turn back into matter. It's exactly what they're talking about. So as far as they're concerned, that is antimatter. This to them is matter. To me, I don't see it that way. The black is the heavy particle. That primarily makes up what matter is. This is just the energy of matter. All right? Basically, the black is matter. The white is the energy part of matter, and they're just glued together. They're the Dirac particles that I showed you. These Diracs right here. There's a black side and a white side, and every single thing there's nothing that's not made of these. Everything there is, 100%. Life, dirt, water, electricity, everything that is anything is made of these two particles, and sometimes they can split. Yes. And here it is splitting. The black is split away from the white. I never thought that could happen, because a power magnet, you can't do that to. The only reason we can do it here is because there's no place left to go. All you got is a black and white. So what are you going to do from there? Although I did find something that was just absolutely stunningly amazing, because I can see all the interactions. I can see all of the Higgs fields. I can see all the stuff that they can see at CERN. We can see the green versus the red, how dim the red is versus the green, how powerful the green is. It recombusts out here. The red is done. Both of them going through the same slit at the same time. And, we can see the particles. We can see the light spins. It doesn't flap like a wave. It spins like a circle. This is exactly what light does. It's just like this. And as it goes, sometimes it goes that way, sometimes it goes this way. It's a single slit. That's what light does. It spins. It doesn't just flap like this. So anyway, I think I've made my case pretty well. And seeing light coming from the universe, coming through us from the universe, there's fields everywhere. They have to come through these fields. Those fields are going to slow these things down. Anytime you come through a field, the light will slow down. Light speeds up and slows down very, very easy. Coming through these fields, anything that has a field of its own, which everything does, is going to oppose those fields, and it's going to slow that light down. That's what the redshift is all about. They're spending literally billions of dollars looking for those. We found it right here. Here it is right here. Here's those fields. Anything coming through there is going to have to push that field out of the way. That means it's slowing down. Light coming to us, you're never going to be able to know where anything is in space, because space, first of all, is not homogeneous. Secondly, wherever there's fields, it's going to slow things down. So light is going to shift to the red, absolutely, no question about that whatsoever. But it could be shifting to more of the red here than it is over here, or such and such. So anything you reach out to see how far it is away, you have absolutely no idea. I don't care what anybody says. If you can prove to me somehow that you can see through these fields, which you cannot, it's not right. Everything's wrong right now in physics, 100% wrong. The periodic table's got to change too. All right, that's not just one proton, that's 1,823 of these. By the time you get up into here, you're to hundreds of thousands of particles make up these bigger atoms, which gives you so much diversity and half-life and isotopes and enzymes to work in that realm to reduce life. You have to have that much particle interaction, and it all happens with enzymes in the body. You get nucleophilic substitution just like that. Done. And that's what tears apart food and kills other invading bacteria and everything else, is these enzymes. And they work in this extreme high-end realm of particles, interacting particles in their half-lives, breaking down to stability or breaking down to something that is just devastating to attackers, or breaking down to something that will break your food down. All right, so it's a very deep web, but it's biological too. So all these particles, because you're made of the same thing. You're made of these exact same particles. Everything in you is made of that. There's nothing that isn't made of that. So they all have to. The bacteria basically controls a lot of your life, believe it or not. It creates all of the enzymes that do all the chemistry in your body. Your body does no real chemistry. Your pancreas and your liver and your heart and your lungs and all that, they move around things, and they have enzymes in them, but the only way the enzymes are created from bacteria. So there's a lot more than just particles here. I work through every realm. And that's why I'm excluded from any realm, because the things I have turned up change everything. This is just not right at all. Not right at all. The only thing that exists is the red, blue, and green, and the black. That's all. There is other colors, but primarily we can only see these three because we can create those three. And, it depends on how fast the frequency is that's bouncing back at you. That's why you see all these different colors, yellow and blue and green and orange and red. They're all different frequencies. But when they smash these, they have no idea what they see. We smash ours, we're smashing particles of light. We're smashing these particles right here, which they see, but they don't know where they come from because it's just starting with too big of particles. And these massive, gigantic projects of trillions of dollars they've spent, that I think I have some answers to. At least I have something to share. I would, and I have been literally told to stay away by these people right here, Family Lab. He says, "You're a tinfoil hat guy. Don't ever contact us again. We won't take 1 minute to look at anything you present, because you're a tinfoil hat guy." This is what they told me. So this is just going to go on forever until somebody pays attention to what I'm showing. And they're just trying to make it too exotic so they can make a lot of money doing something. I want to make it so simple that anybody can have this almost for free. These should be cheaper than your cell phone and create as much electricity as you could use. Don't forget, these can be so microscopic. You could have thousands and thousands of them in here, and you could just run as many as you needed to put out whatever you needed for electricity. Simple as that. And the increase in energy should be exponential. That's what they claim. They claim you can get from starting with millions of electron volts, you can go up to trillions. The increase is exponential, and that's all we want is the white energy. That's all we want is the white part. And that's what we did, was we separated the black from the white. And the white should just be able to be pushed right down into our batteries or right out through these devices, through a regulator, and it just goes out that whatever energy you need to use to drive whatever you need. And I don't see them having to be much bigger than that to create a hell of a lot of energy. If they're right, And it wouldn't take more than a couple of weeks to tell one way or the other, is this going to work and how good would it be? And then a little tweak here, tweak there, and you got some serious energy that's portable, cheap, and free, and everything else. Solid state. You should be able to carry these around, run boats and planes and airplanes and cars and heat your house and do all the things we're doing right now by burning oil and fuel and gasoline and all that other stuff. And all we want is the white part to push down into our batteries. So basically this is it right here, feeding right on down into the batteries and put the solar collector there. Last word, I love you all. Hopefully somebody will get a hold of me. I've been trying to get a hold of everybody. I tried to contact the guy from CERN that had that article I showed you about antimatter. Well, it's rare. Well, we'll see what happens. It would be nice to hear from somebody to have some interest in what I'm showing. I think I've presented a pretty strong case. And it would be interesting to see if anybody is actually interested in developing this. I got to be honest with you, this is so frustrating because I just never got anywhere with the people that I thought were interested in the development of all these kind of things or understanding things. That's not the main goal that I see. Now, maybe they're going to be different, this guy that I'm contacting. He's talking about antimatter, all this stuff, and I think I've shown at least something that he may be interested in discussing. And anybody that's in a physicist, I had somebody on the other day. Well, I'm a physicist, and we know that light spins, and light only goes the same speed. It never speeds up. It never slows down. I said I showed you all this stuff. How can you say that? And that's it. No more conversation. That's it. They're done.